Welcome to 24 hours of PaaS evolution of the data platform. We are excited you could join us today for Robert Dorr's session, SQL Server 2016 just works faster, performance improvements in database core engine. This 24 hours of PaaS event consists of 24 consecutive live webcasts delivered by expert speakers from the PaaS community. The sessions will be recorded and posted online after the event, so you can access them on-demand sessions by visiting www.24hoursofpaas.com for all session links. My name is Satya Shyam Jayanty. I'm a data platform MVP, and I work as a solutions architect within the data platform area. I've been using SQL Server for past 18 years now, nearly. So, and I'm glad that you could join us today. Before I hand it over reins to Robert, I have a few introductory slides that I would like to kind of go through with you all. Okay, in terms of for the technical assistance, if you require any technical assistance, please type your question into the question pane located on the right-hand side of your screen, and someone will assist you. We'll get to that. And this question pane is also used where you may ask any questions throughout the presentation. Feel free to enter your questions at any time, and once we get to the Q&A portion of the session, I'll read out your questions aloud to the speaker. We'll accommodate as much as we can based on the time, and also you can also zoom the presentation content by using the zoom button located on the top of the presentation window. And please note that there will be a short evaluation at the end of the session, so I would encourage your feedback that will help us. So please take a moment to complete it, so it will appear in your web browser. So based on that, it will be very useful for us. And before that, I would like to take a moment to thank our presenting sponsors, Microsoft, Amazon Web Services, Redgate, and Hortonworks. Hortonworks develops, distributes, and supports the only 100% open source distribution of Apache Hadoop, explicitly architected, built, and tested for enterprise-grade deployments. It is the only Hadoop-based platform available in both Linux and Windows. So also I would like to thank our supporting sponsors for this event, Hewlett-Packard Enterprise, SQL Sentry, and SanDisk. And the staging of this 24 hours of PaaS would not be possible without their generous support, and they are the reason for this event. We could able to make it free of charge. Right. Make sure that you explore everything else PaaS has to offer for data professionals. The summit, which is scheduled this year, October 2016. You can also join your local user groups around the world. So sqlpaas.org, you can find a lot of information. You can find free online resources through the Learning Center, and also you can read the latest community news within Connector newsletter. And you can visit whichever local chapter you are interested to join. That will help you.
Well, welcome.
Here we are. Sorry, Bob. Before I just okay. I think I think this is where it is. I would like to hand it over to Bob, and there you will hear from Rob about the session. Over to you, Bob. Thank you.
Thanks. Hi, everybody. Welcome to the session. I'm pretty excited, actually. This is the first time we've done this publicly after the blog series to take you through not necessarily all the different changes we made, because it's way bigger than I could squeeze into the format today, but some of the history as well of how we got here. And why this will be some of the fundamental changes that took place with that. So with that, I'm a SQL professional, been with Microsoft since '94, supported SQL Server in various capacities up until March when I joined the actual dev team. So I'm now on the dev team. I own some of the things that you're probably heard about before in the SQL OS space, scheduler and things of that nature now. Had various utilities that across the spectrum. And before I joined Microsoft, I actually worked on SQL Server on OS 2 on a PC environment at State Farm. So I've been here for a while and kind of know the ins and outs of what's here and what's good and what's bad. And as Satya pointed out, feel free to load up the questions in the chat as necessary, and we will try to answer as many as I can today as we go. So as I mentioned, I want to talk about the history of this a little bit, that this didn't just occur that 16 just works faster. And this is outside of the standard TPC type benchmarking stuff that you're used to. While that's still part of our system, the way the databases are judged, the way databases are marketed, all that stuff, TPC, Cs, TPC, H and stuff all comes out there. This was a different effort. This was actually a customer experiences and issues driven problem. Back in 2014, calendar year 2014, we actually saw quite a bit of ramp up where the system really tipped from just getting faster CPUs, going from 2 to 2.5 to 3 gigahertz CPUs, into multi-node, might have actually been slower CPU, but lots of parallelism, that sort of thing. And some of that had been designed for in the space of 2005, 2008, 2012, but we were finding that as we started getting up with more than 8 cores, more than 10 cores, that sort of thing, that all of a sudden some of the designs that worked well on an SMP box don't work so well anymore. And it kind of actually took us back, clear back into the late 90s and 2000s where the SMP boxes started getting 16, 20, 24, 32 CPUs on them, and we were seeing some scalability issues in there that had been addressed by kind of divide and conquer. One of the theories at that time was, hey, and it still holds true, but you divide and you conquer. So if you divide things out into per node or per scheduler type lists, that sort of thing, you have a smaller list to maintain or a smaller cache to maintain, those sort of things, you can get better performance. But at the same time, you can, if you start doing that too much, you can start sacrificing, because if you have to go get an exclusive lock across everything, you have to go get multiple locks across each scheduler or each node or whatever the partitioning scheme might be. And so you kind of can run yourself into the other end of the spectrum. So what we did is actually we were talking to Rohan. Rohan is the group program manager in charge of SQL Server. I've known Rohan actually since he was a lead that helped install the original file streams activity in SQL Server. Really nice guy, and we talked to him, specifically myself, Bob Ward, Keith Elmore, and a few others around here. Talked to him and said, look, we've got a whole list of things that don't work well when customers call in, and they're calling us with what we call crit sits or severe errors, server down type scenarios, and we're just turning on a ton of trace flags. We're doing a lot of configuration things, doing all this stuff that we can get SQL 12 and SQL 14 to work in this environment, but it's not clean. It's fairly painful, to be honest. And so he said, look, put that together, come up here and see us, get my architects and my leads in a room and explain to them this problem. And so I actually, in September 2014, took a white paper, went up there and spent a week, and that's exactly what I did. I went through a whole bunch of these scenarios with these guys in the room that have built SQL and know SQL inside and out, and said, hey, this doesn't work. The customers are seeing these kind of problems. And out of that meeting, what actually came of that was a new or a reinvigorated team on the development team. They brought back a guy named Ryan Stonecipher, who maybe you guys know him, but he wrote DBCCs, and he actually was in support for a while. Slava came back into the mix, some other things. And they actually took, and part of the perf team, they developed a new arm of that. And that new arm is designed to do what I'll call real-world testing. Yes, we still do, like I said, the TPCC, the TPCH, and all that kind of stuff. But this part of it is, no, how does it actually work on, can we do it in Azure? Can we do it on a production system? What are these things? Can a customer actually use this thing versus, yeah, it makes this really high-end scale thing if your app is written just right with just the right pattern. Most apps, as you all know, don't, we've got this guy that runs this Excel report and it's not very good with locking, or we got this person over here that wrote this old app and we can't really update it, or it's an ISV. That's more the real world. So what we did is we targeted over 60 work items at that time. There's much more now. I think we're up to about 180 total that we've got targeted. We target a bunch of these work items and said, look, let's rank these and prioritize them as from customer pain standpoint and experiences standpoint, and let's go after these things. Let's go fix these things and make it where if you just put SQL 16 engine on the machine, you don't change your app, you don't do anything else, you should get a couple of things that it should run faster. You should end-to-end duration of the query or process you're running should be faster, and it should use less resources. So how do we shrink the memory footprints, and can we run it faster on a single thread than on multiple threads, or can we make it do things better in parallel? What can we do to do that? As part of that, we developed a new test suite, and that's internally called Trevor. That's actually Robert spelled backwards because I did the work, and I picked that out of a scenario. And what that has is a bunch of test suites that actually I took over a 3-month time frame from September on. Every day I would add a new test to this test suite. It was just a goal every day to add a test. So by the time January came around of 2015, we had this test suite that had all this stuff in it that you guys have run your head against. Somebody open lots of cursors, do prepared statements, do lots of cancels, throw deadlocks at it, things that are what I'll call more real world. And that, by Ryan's team took that, he and his team took that and built that in, and we do perf runs on that as well. And that's part of our sign-off criteria now. We actually have to run these Trevor test suites that are not what you would typically think about as just this benchmark suite. That you can't really, it's difficult actually in certain cases to benchmark that when you're running all the different patterns together. You can run them singly or you can run them together. When you run them together, you're causing all kinds of different things, but the overall end-to-end workflow and things we measure and make sure that we don't regress something. So as now somebody checks in, this runs in the background all the time. Somebody checks in, we don't regress. DBCC now is taking longer instead of shorter, or when we make those changes. So we're catching some of these things way early. So that's kind of the core history that took place with there. And as I mentioned, there were several driving factors. The increase in CPUs per node. Once you get past 8 CPUs per node, some of the typical programming designs and algorithms you use have the same problems that we used to have in SMP boxes. For example, there's a thing called a spin lock that's used fairly regularly throughout both Windows and SQL and other things. And what that is a way for you to essentially flip a value in memory with the interlocked instruction on the CPU, and you can spin on it waiting for it to go back. So you flip it to 1, you own the lock, you flip it back to 0, and somebody else can acquire the lock. So in small code paths, like I want to add just a single node to a linked list, you might not go through a complete wait, you'll do a spin lock and go through there. Problem is once you get more than 8 guys spinning, you only have one winner. So if you get to 9 or 10 CPUs, you have 10 guys spinning, 9 losers. You get to a 16-way system, and all of a sudden you get 15 losers. And so the number of losers just starts burning CPU that's not conducive. So you need to look at partitioning those structures or coming up with a different way of doing that so that you don't have to sit there and spin and spin and spin and burn CPU. And I'll mention some things about one of the factors here in a little bit. Larger memory footprints, big deal with both I/O and memory got bigger. SQL 16 can run on the terabytes and terabytes of RAM. You can't be doing standard things of just scanning the buffer pool like an old checkpoint did and be efficient at it. So you'll see we'll talk about indirect checkpoint here in a little bit. High-speed I/O, a lot of times there were a lot of code paths that you could assume that when you did an I/O, it was going to take a little bit, whether that's 2 milliseconds, 4 milliseconds, whatever, but it's not nearly, that's a huge amount of time compared to the CPU time for running instructions. However, now that you've got your flash and your fusion and those sort of devices around, the I/O in a lot of cases completes immediately, and especially with the newer stuff that we can do with non-volatile RAM, it's just a memcopy into the non-volatile RAM. There is no more I/O latency, and so those kind of code paths where you could write them expecting that you get I/O latency don't work very well anymore. High-speed networks add to there, and then just data explosion in general, that certain things you have to think about their usage. Spatial is the number one I'll kind of throw in here as an example. Nobody builds a scenario to track things for spatial that doesn't have all of a sudden millions and millions of rows, because you're tracking something. You're typically tracking some kind of car movement or whatever it is, and all of a sudden you've got millions of rows. Well, we have to make that partitionable and and the right indexing schemes and the right parallelization schemes, and all that has to work, or it doesn't, the feature, yeah, you have it, but it doesn't scale very well. So we went through a whole bunch of those kind of things. So let me kind of give you the highlights here. And again, there's no way I'll be able to cover all these today. I'm going to pick a handful of these and go through them. We will continue, Bob Ward and I have already talked, we will continue adding things to the series as we get time to add to the series that's already out there on PSS SQL. But there's kind of two categories that we think about this when we think about this. We think one about just core engine. That's kind of the left-hand side of the screen here, that no matter what you do, you're probably going to touch on a good portion of these will be helpful to you. The right hand of the screen is what I'll call more pick list type things, that if you're using Spatial, you will benefit. If you're using, for example, always on, then the availability group compression and transport is important to you. So we've kind of got two forms of this that we've kind of laid out here a bit. Some of them have some overlap, but for the most part, that's kind of how to look at this slide. So as you can see, we've gone through all kinds of things, DBCC and TEMPDB schedulings, and we'll talk about file sizes and how we do files and the number of log writers and internals like the reader-writer lock, parallel recovery and that sort of thing, are all just built into the SQL 16 engine. And what we're seeing is that pretty much our CAT team that brings in customers and does advanced deployments and analytics with customers, on average, and your mileage will vary, of course, it's not something I can hardcore stand on, most customers can upgrade the server, just the SQL server itself in place, no new hardware, no app changes, nothing else, and typically get about a 20% resource reduction of both memory and CPU in general, giving them a lot more room to, hey, if I can get 20% back on the server, then I can add 20% load. And because it runs faster, I might actually be able to get more than 20% than the original 20% load. That may equate to some mathematical value, say 28% load or whatever. But you're getting essentially stuff for free just by upgrading the thing. All of a sudden the app gets better. Things work better, that sort of thing. So with that, let me take you through some of these specific changes we made and kind of some more details around each change. I want to start with DBCC because that's one that pretty much everybody in some form or fashion will touch on DBCC. And one of the running jokes has been around here for years, because we work cases where customers will call and you guys once in a while run into a corruption scenario for whatever reason, be that a hardware scenario, lost drives, there's been a handful of bugs throughout the years that SQL has introduced it. We always run DBCC in that particular avenue to figure out what the corruption looks like, and that question is always like, how long is DBCC going to take? And the answer has always been it takes as long as it takes. And unfortunately, the answer is, it's kind of funny and it's kind of not. That I don't know how long it's going to take because I don't know your data and I don't know all the internal structures and all that kind of stuff. But once you get DBCC running on your machine, you know how long it takes. And what we found is that DBCC simply wouldn't scale. That, as you can see from this chart, as you started adding more CPUs on this terabyte database, the red line, as it went out, simply didn't scale. You get out 64 CPUs, and it took forever compared to the smaller number of CPUs. So it sounds strange, but why would I want to use a smaller number of CPUs to go through a massive scan of my data? So this is actually one Ryan worked on, and he switched out what's called the multi-object scanner. Essentially, internally, what we have is you have the ability to run a parallel scan of various pages and objects within the database. And as you're doing that, you go back to this multi-object scanner and say, tell me the next page I should work on. So you start up a bunch of threads and they start working. The first one comes up and maybe it gets page 1. The next one comes up, maybe it gets page 2, starts doing its thing. Well, that actually was a contention point. As you started adding more CPUs, you started getting everybody colliding on that multi-object scanner. So it just so happened that Ryan also had done a bunch of development work inside of the in-memory optimized database engine with SQL and understood the primitives for in-memory optimized and how you could do some of these things without having to take out these heavy locks but still stay synchronized. And so he ported that into and changed the multi-object scanner to a check scanner object that is based on the in-memory optimized database engine primitives. And so as you can see, on the low end, it's fairly similar in 4 and 4 CPUs. As you get to 8, you're almost, 40% less, but then you see we drop down as you get out to 64 CPUs on a 1 terabyte database. You pretty much you can see the difference here. It's 7 times or more faster to do the same DBCC on the same database if you just put SQL 16 on the machine, which immediately means to you all, I shrink my maintenance windows, which I know that comes up time and time again is a huge issue, that if I can shrink my maintenance window, open it up for more backups, open it up to do X or Y or Z, life's a lot better. So that's one of the first ones I love to talk about because it's so simple. You don't do anything. You apply SQL 16, it picks up the new code base. The new code base does this for you. It's just simply faster. TEMPDB is another one that we targeted, as it is fairly painful, as you all know, to configure it. So there's a couple specific things with configuration that I want to touch on, this metadata access that comes up, because that's the one that really excites me. So a lot of you are used to having to turn on trace flag 1117 and 1118 so that you can do even file gross and use uniform extent allocations. That now is the default in TEMPDB. You don't have turned on anymore. Whenever you apply SQL 16 to a box, you simply get uniform allocations with uniform growth in TEMPDB. And 1117 and 1118 was also ported into a alter database command so that you can do it on a per database option for user databases, so you don't have to turn it on and all of a sudden all databases grow or all databases take on this behavior. You can cherry pick the way you want to. The other thing is that we changed the setup so that it will accept information to allow you to create the multiple files and some of these size things, as you can see here, about initial growth, initial file size, that sort of thing, up front. So when you go to install these or roll them out or set up your rollouts and that kind of thing, you don't have to come back and write a separate script or a separate action to do all that work. So by default, when you install 16, it's going to try to do multiple TEMPDB files, allow you to do uniform and auto grows with a sizing scenario here so that you don't have to immediately run over the machine and say, hey, I've got to configure this to even make it work right on this 8-proc box or 16-proc box. The other thing they found was really interesting. As part of this effort, we started doing additional internal, I'll call it telemetry. We started looking at code coverage and how long it took to run certain code paths. We always done that, but we kind of doubled back on it with the Trevor test and said, hey, what's going on here? What of these things could be better? Could we get through this code line better, faster, that kind of thing? And one of them we found is that anytime you touch temp table and you're going through it, there's a specific code path that could potentially have to do an update to one of the system tables. But in the majority of test runs and the majority of customers we looked at and the majority of activity taking place on Azure, less than 5% of the time did you need the update latch. So you would go through there and determine that I don't need to do this update. I just need to check to see if I need to do it, but I don't necessarily need to do it most of the time. And because we were taking an update latch out, that made everybody serialized to go through to check to see if they needed to do the work. That has been changed to a shared latch to let everybody scan in parallel through that, and only when you have to lock it down, that 5% of the time, do you have to go acquire the update latch and make the change. Made a major difference in trying to access the metadata activity for TEMPDB. So you get rid of some of the headache that you guys have seen with TEMPDB, and again, you put SQL 16 on, you get the metadata latch thing. It just works. It's just faster. Automatic soft NUMA is the next guy here to talk about. There's always been a concept since 2005 of soft NUMA, and what that is essentially you take your CPUs, your scheduling information, and you can divide it the way you want to, so it doesn't have to match the NUMA node configuration that's on the physical machine. Well, what we found is, again, as we start getting past 8 CPUs per node, we started running into these SMP problems. But the engine had a whole bunch of things done clear back in 2005 and continued through 2008, 12, and 14 builds that would partition logically by a NUMA node. So query plans go to NUMA nodes, lock resources go by NUMA nodes, on and on and on. This engine had all this stuff, and if you would just tell it that it had more logical nodes, it would partition more to a reasonable degree here. You could split say you go get a machine that had 12 cores on it, or 12 cores per node that were hyperthread enabled. You have 24 CPUs in that one node, and all of a sudden you've got, this hotspots coming up. You're way past 8. But if you divide that by 3 and create 3 nodes, you could partition all this stuff, and a bunch of things in the engine take off. You get a resource monitor per node, you get a scheduler monitor per node, you get lock association, you get just on and on and on. There's dozens and dozens of places. So but one of the complaints with soft NUMA is that it's a registry thing. It's actually pretty hard to set up in the registry if you've ever tried it. It's fairly tedious, and it applies to all instances on the machine once you put that out there. So instead, we changed by default, and it's controlled by SKP configure. You can turn it on and off. If we see more than 8 CPUs per node, we will go ahead and automatically configure a soft NUMA configuration internally to split the nodes up as close to 8 as possible and trying to keep even nodes, and try to make sure that we also are not placing logical CPUs and physical CPUs from the same core within the same node, so that you don't end up scheduling everything still on the same CPU. So what you end up with is immediate partitioning of the engine. When you go into one of these bigger boxes, immediately SQL detects that and says, hey. And as you can see from the numbers up top, a large gaming company actually came into our lab, ran a test, and it ran 400,000 batches per second. They went to SQL 16 with AutoSoft NUMA disabled. It immediately jumped to 0.74 million batches per second. So just 16 on and of itself, with all the other changes that are available here, almost doubled the number of batches per second they could do for throughput. And then when you let automatic soft NUMA kick in, where it did the additional partitioning, we jumped up to 1.2 million batches per second, which I was actually tracing that with XEvent, and that's just crazy when we were seeing the amount of data coming through the system. So another spot where we just detect, this is what the system looks like, we should do this, the admin and the end user shouldn't have to care about it, let's just get it up and running. There was a change made way back in March of 2014 that actually got rolled out to all our Azure properties, the Windows Azure SQL database stuff that you're used to seeing from Microsoft. And what that is, it's called deficit scheduling. And so George on the SQLS team went through, and we actually looked at a problem we were having with resource governance and scheduling. And the top right here shows you what I'll call the quantum, or the percentile-based scheduling is a better way to say it. So think of this, think that W2 can only get 10% CPU for the W2. So you put them in a group that only gets 10% CPU. So what we did is we'd say we have this percentile queue concept in 2014, 2012, 2005 that says, hey, if you only get 10% CPU, you only get in the runnable queue every 10 times basically. So only drop them in the 10th slot. So 10, 20, 30 as they go around. But W1, if it's at 100%, it can run on any one of those slots. The problem is that doesn't equate for the time of how long the actual worker ran. And so one could potentially run very short quantums, say less than a millisecond, and eat up its 9 before it hits the 10th one. W2 could come on and actually eat a full 4 millisecond quantum, and so that's really not 10% of the overall quantums at that time. So instead, George changes it and actually tracks across all CPUs within the group, the resource group, what quantums are actually used, and then will reschedule you based on your target quantums for or your target percent based on your resource group and what quantum you have actually used in that group. So what we get in this case is you might see that W1 runs, and then W2, if it had a small quantum, in this case, in the second example, it might get scheduled multiple times, so it's allowed to use its 10% of quantum before W1 gets to come back onto the scheduler. The actual chart below here is wrong. That should be flipped around, sorry. I've corrected that in my local deck, but I didn't have time to correct it on this one. The chart should show you that the same workload that I ran on 2014 actually took 32 seconds, but if you use deficit scheduling and allow it to balance the workload, you can actually run in 21 seconds because the W2 is not getting starved in between W1s by dropping them in. And so there's all kinds of things there. The best part about I like about this is it's been running in our Azure properties for over 2 years. And so it's baked in. It's already there. It's been working and up and running. And again, if you just put 2016 on, you get it for free. Here's one that's near and dear to my heart. CMemThread is a multi-threaded memory object for SQL Server. So those of you who have coded before, looked at something like that, you can think of that kind of like a SQL Server heap where you have to go in and protect it. So when you do an allocate, you do a free, multiple threads could access that same memory object, so you have to have some kind of locking mechanism. And what we saw was that there's just hundreds of these all over the server because various reasons for the designs. And if you would get a certain pattern, one would get hot. A bunch of threads would line up on a single CMemThread. It would get hot. Everybody, and again, only one person can use it at a time, so the more you stack up, the CMemThread is even worse because CMemThread actually yields a scheduler. It's not a spin lock scenario. And so I could actually have hundreds of people lined up behind this guy. The first one comes in and gets it and then goes. The next one comes in and goes, and you just start this big convoy. And we probably had a dozen or so QFEs that I've personally worked on myself from CSS, where we'd find a specific mem object that was hot. We'd have to go to the dev team. They'd go out, and what they do is they would partition it. And so way back in 2005, there is a concept of partitioning a memory object, but when you create the memory object, you have to tell it it's allowed to be partitioned. And in most of these cases, it was told to be a global scenario, an instance-wide CMemThread. Well, there's two other levels of partitioning. There's by node and there's by CPU. And so as we were whiteboarding this thing and going back and forth and kind of arguing about it, to be honest, a little bit about how we should do this, we got to fix this thing. This thing's killing us. It's just the customer can't get out of it. There's nothing you can do about it. It's an internal structure. You'd have to change your query pattern to get around it. And it's not something you can just immediately turn off once you hit this in production. And if you turn on trace flag 8048, that only allows you to partition the ones that are already allowed to be partitioned by node, which are only about a half dozen or so of those in the engine anyway, so it doesn't make this massive amount of change. There are some that it helps, but it's not this like hundreds of them just change. If it was marked as instance-wide, that's what it stayed. 8048 didn't happen. So what we did is we said, wait a minute, we've got the concept of latches that will automatically update to a super latch. When it detects contention, it knows, hey, this one's being contended. Let's go ahead and split this thing out to a per CPU or a per node basis thing. And so we took that design concept and they put that into the CMemThread logic. So when CMemThread actually is doing allocations and deallocs and weights and all stuff as it goes through that code path, it's actually watching that now. And as soon as it starts getting hot, it will bump up the partitioning. It will automatically, internally, dynamically go, hey, I'm going to go to node partitions. Let's have one per node. It takes a little bit more memory, but it makes a huge difference in how fast you can get through the latch or the memthread allocation logic. And so at that point, we continue to monitor it. If it's still hot, we will bump it up to a per node. So as the chart is showing, is we're running along, and we show you throughput is the green, and the latch the contention is the red here on the memory object. And so we ran a load here, and we actually internally prevented it from, in our test lab, we prevented it from being able to dynamically upgrade itself. So we ran along and ran there for a while, and you can see we're getting lots of contention, and our throughput, you know, is chunking along there. Then we allowed it to go ahead and dynamically partition, and you can see the dynamic partition happen, and within a very short window here, a few seconds, the server immediately basically almost tripled the throughput, and the contention is essentially gone by the time you get out to the 55 AM. So within 30 seconds, the server had figured it out, configured itself out, and let that server run way, way faster. And so if someone comes on and throws a new workload on your server and it happens to hit a different one of these 100 or so odd CMemThreads, and all of a sudden that memthread gets hot, it just dynamically partitions it behind the scenes for you again, and off you go as a DBA or an admin or something. You don't have to worry about it. It's just going to do it. It just takes off and does it. And again, this is another one of these where throughput just dramatically changes nothing you did in your app. I mentioned earlier the memory footprints. Memory footprints, as I got larger, made certain things a little more tedious. The design didn't hold up over time. So one of those, it happens to be Checkpoint. Checkpoint, when that kicked in, would simply start at the beginning of your buffer pool, effectively, start at buff 0, and start scanning all the buffers, looking for pages that belong to that database that are also dirty within the right checkpoint generation and flushing them to disk. So when we were testing on a 12 terabyte system internally, we were creating pubs and found out that pubs was taking minutes just to do the create phase. And so as we started studying that more, we noticed that what was happening is the scan across all the buffers just to check to see if they belonged to pubs was what took the majority of the time. That if you go scan 12 terabyte worth of buffers, you're going to go through millions and millions of buffers and do all the lookups and the latching and all the stuff that goes with that. You're using a lot of CPU. It looks really cool when you look at the CPU code because it's, you know, hey, we're pegged at 100%. Yeah, that looks really good on a chart. But all those CPU cycles are useless because they weren't, the number of pages you actually dirtied to create pubs is dozens, maybe 100, not 12 terabyte worth of pages. You don't need to look at them all. So back in 2012, they started working on this. 2014, it's really solidified. There's a concept called Indirect Checkpoint. You can turn this on in 14 if you go to each database, but this is the new default for new databases created on 2016, so you don't have to worry about it. And what it does is internally we have to track dirty pages anyway. So every time we dirty a page, we're just linking it off of a list for that database. So when checkpoint needs to run, if you have indirect checkpoint enabled, it simply goes to that list, yanks it, and says, here are the n number of pages that I need to checkpoint. Run that list, write them off the disk, and checkpoint's done. And so all those CPU cycles to go through buff after buff after buff after buff are gone. We don't have to do that. We know the exact buffers that have to go there. We don't have to do this buffer pool sweeping to make that happen anymore. And so hence the indirect checkpoint being the default for SQL 16. As you start, you know, more and more machines, you start seeing terabyte, 2 terabyte, 4 terabyte, 8s, and those sort of things come along. This algorithm is much more suited to allow that to perform well for you. Another space that has been problematic for lots of you for years has been the log writer. By default, prior to SQL 16, when you started up a SQL server, your log writer typically ended up on the first node, usually within the first 4 CPUs, typically based on the way the workers are created in SQL Server, and they shared the same script as other queries taking place there as well. And what we found was most of the time that's pretty good, because this is one of those areas I mentioned to you where I/O took a long time. 4 milliseconds is a long time, as I said, in compared to just doing CPU activity. So start looking at this when you went to something like a flash-based scenario or a in-memory NVDIM or Fusion, or one of those kind of scenarios, and all of a sudden LogWriter is more CPU bound than it is I/O bound, because the work that LogWriter is doing to fix up the log block, format it, maybe compress it depending on what's going on. You may have encryption, and then come along and wake up the users for LSNs that have cleared, so that users waiting for LSNs to finish commits or rollbacks have to be woke up. All that work is CPU bound. And as we looked at that, you essentially could start consuming more than one CPU on these high-end machines. So in SQL 16, what it'll do is detect if you are have a machine that has multiple nodes, and if you do, we will create up to a maximum of 4 log writers, usually on nodes 0, 1, 2, 3, and 4. And so they simply share that same responsibility that log writer has always done. They still do the same things, they just share the same list. You in queue request a log writer, it picks them up on the backside. You just have 4 parallel log writers picking up the requests and doing the work for you, spreading it out and being able to do CPU across 4 separate CPUs instead of it all being bound to one CPU. And so on those high-end machines, you can see throughput of transactions, specifically inserts and updates, because they're using the log, of course, are just simply, you can run them harder, you can run it faster, and again, just another thing that if you upgrade the engine in place, you can get multiple log writers. You can push these types of subsystems way better than what you would have in a prior version of SQL. Spatial, this one's kind of another one that's near and dear to my heart. The guy who was doing Spatial actually a couple of years ago retired, and nobody was doing it, and so all of a sudden say, hey Bob, we have a problem here, we got cases with spatial, and I started answering questions. And this is one of these that I found that, like I mentioned earlier, nobody does a little bit of spatial. Everybody that starts into spatial, all of a sudden, oh, I've got 300 million rows. I worked with a company out of Uruguay. Oh, we got 1.2 trillion rows, that sort of thing. And when you start doing that, all of a sudden things like index maintenance and filtering and all that stuff becomes very, very tedious and on the spot. And so we started looking at it, and essentially what we found is when spatial was built, it was built that you could use it on the client or you could use it within the server. And so what they did is most of the spatial stuff is actually contained in a DLL that's written in C++. SQL Server Spatial, version number .dll. And that is actually wrapped with an a .NET wrapper class, so you can use it in .NET. Works really cool. You can call toString, you can do all the stuff, and it just works for you. You can do it on the client the same way you do on the server. The store procedures on the server look very much the same as they do, or the T-SQL looks almost identical to what it does in your .NET client. Everything's really cool. The problem is that interface between SQL Server is written in C++ native C code. Then it has to p-invoke and p-uninvoke in and out of the .NET layer just to call a native DLL. So that was one of the places where the team, Greg specifically, did a lot of work in here, went through all these functions you see here and brought those back into SQL to call the DLL directly. So essentially they are natively inline, and we no longer have the p-invoke, uninvoke stuff that takes place with that. There's been various other fixes we found where we could do tessellation better, we could do filtering better. The line string now does a vector sort, which makes it completely way faster than what it used to do before. And as you can see the numbers on the right, you can see like the TVP fix, you could go through 8,000 rows per second inserting if you had a TVP that had a column with a spatial data type in it. If you apply SQL 16 and that TV or the TVP fix, there's a handful of these that are available to you in 14, and a couple of them that actually got backported to 12. You actually can jump up to 120,000 rows per second. And that was simply just a simple thing where if you looked, we weren't caching the assembly properly for handling TVPs. And so every row required us to reload the assembly. Well, that's just going to be really slow if you have to reload the assembly every time. And so simple fix. It wasn't anything that the end user did wrong. It wasn't anything your code did wrong of binding anything correctly or sending the TVP with spatial columns. All that's supposed to work. It just simply didn't work at scale. And so another one of these areas where Trevor actually, we beat this up and said, hey, we got to go fix this. And so if you're using spatial, go ahead.
Yeah, sorry. Yeah, we have 14 minutes to go, and there's a few bunch of questions, so I'm just kind of reminding.
Okay. All right. I should be. Let me double check here. I think I'm about to the end of what I tried to hit today. So, okay. Yeah. All right. Yeah. Give me about 5, and then we can do questions.
Sure.
Vector instructions is another one we built in. So I'll touch on this briefly, but basically vector instructions allow you to off the CPU allow you to perform operations on more than one piece of data at the same time. So for example, you can perform it on an array. So if I want to go through a byte array, I could use a vector instruction and actually do the same instruction across 128 bits or 128 divided by the 8-bit byte all at one time. And so what that, in areas like compression, encryption, column store, bulk insert, those kind of areas, we can use the hardware speed instead of having to use software conversions on that stuff. And so things are way better. Like if I want to take a string and convert it to an integer value, so say you got the value 1, 2, 3, 4 in a string, I can actually convert 1, 2, 3, and 4 all at the same time with one instruction to the CPU instead of converting 1 and then converting 2 and then converting 3 and then converting 4. So you can mathematically do that way faster. And that's built in when we detect that the software or the CPU provides SSE or AVX capability, we will automatically route to that instead of using the software equivalents that we would typically have used in 2014 or 12. Always on, they made a huge amount of work in always on. So this is one of these pick list ones I told you about. If you are using always on, there's just massive amounts of performance improvements they did in this space. Reducing the number of context switches to send a log block by 5 times, using parallel compression instead of a single thread to compress. They actually pulled in a different compression algorithm that is only takes 2% more CPU, but you can see the throughput numbers it gives you. You jump from 82 megabytes per second to 540 on this particular test box. And then they built in parallel recovery so that when recovery is running, that's just not always on. That's one of those that parallel recovery can happen, period, on any version of SQL. So you can actually crash, any crash recovery comes back up, but specifically for always on, when you're sitting on a secondary, being able to run parallel recovery can keep you up to speed and up to date with that. And then again, when we can detect that the hardware on both ends of the side of this will support hardware encryption, we use that, which is 20 times faster encryption than doing it in a software-based scenario. So there's those combined, you're always on is, I really like it. And then there's things like this that we even did on the client end. I put this one in just to kind of show you. The Linq reader itself had a problem where every time you go after an event, it would go after each column, and it would have to do some transitions and things underneath. The same guy who worked on the spatial thing helped work on this one, and again, we went from reading 8,000 events per second to be able to read 80,000 events per second. And you can get that .NET class just picks that up with the .NET Linq provider, and when you're looking at this like in Management Studio, it just opens that much faster. You can scroll around that much faster. You can sort that much faster. All that stuff is just faster. So it's not just the engine we went after. We went after kind of your ecosystem as we came through there. And finally, we're continuing to do this. This is not something that was just 16. This is something we're continuing to work on every day. I just saw a thing going the other day for sort memory object caching, so we can, when you're doing sorts, we can cache the memory objects better. We're looking at porting the compression algorithm into backup restore so that we can get faster compression at the same ratio with minimal change to CPU. There was a reader-writer lock, spin lock design that's been tested, and it's actually right now going through finishing up test phases now, but basically when you go through spin locks that need to search, you don't need to have a spin lock. You need to have capability of going through read as a reader, like a shared scenario, or an exclusive if you want to make a change. That again is another one of these spots where things scale way better. I think they gained 12% in this one code path for this particular customer in that. So we continue to do this, and we got a whole bunch of other stuff stacked up as well. So that's kind of my quick and dirty. Let me answer some of your questions since we got a few minutes left.
Sure, yeah, we have 20 minutes or odd. Here's a question from Glenberry. Do you have a plan to have a wrap-up of the CSS blog series, or perhaps a white paper that covers the performance enhancements in SQL Server 2016?
So there is a bit of that. We are looking, Bob Ward and I are looking at going and collecting all this into one spot. This presentation is one way of starting that, of getting this all in one spot, getting one set of slides together for this and putting that all together. So the idea is, or the short answer is yes, we have some plans. The longer answer is we just have to execute on them yet.
Okay, that's good. Another question from Raj Kandaswamy. Is it possible to configure SQL Server analysis services and reporting services to limit memory?
So there are configs on those particular services. I'm not super familiar with them that I could rattle them off on the phone for you today, but I know there is a config file for RS, and I know Lisa, who sits beside me, has talked about it, so I know there are ways of doing it. I just can't tell you off the top of my head.
Okay, good. Next one from Sergey Maslow regarding TEMPDB sizing. During SQL Server install, why are default initial size and auto growth so small? Also, does the installer allow the set auto growth to say 1024 MB? I heard it did not in CTP3.
Okay, so we picked those numbers based on virtual log file sizes and a bunch of telemetry that they looked at as well off of our Azure install base. So from that standpoint, there's an argument to be made that those are too small for a standard enterprise scenario. What they were supposed to have done, I haven't tested this myself, and if it's still broke, we probably need to look at it. What they were supposed to have done is make that so that you could configure like he's asking, from both the GUI and the command line, that you could feed it in and tell it, hey, I don't want 64, I want 512, or I want 1024. If that doesn't work, it's something we should just follow up as a bug.
Okay, and there's a question from HK. Does the automatic soft NUMA also benefit the VM guest with 4 vCPUs?
Yes, it can. So we simply look, we make the calls to the OS to say, tell me the number of NUMA nodes, and then we also do some other information to tell me get logical information for the processors, which is a combination of both a operating system call, and we try to use some of the CPU ID instructions on the box to figure out, is this really the same logical and physical things on the same CPU or not? And so if we see that and essentially once, we won't even look at it if you don't have more than 8 CPUs. If you're configured for less than 8 CPUs, you don't have 8 CPUs, we don't even look at it. It's like, okay, it's just a standard SMP type scenario, leave it alone. As soon as you get past 8, it should start looking at that information and start doing that. And it adds outputs into the error log to show you what it's been doing and kind of how it's configuring. So you should be able to watch that come right through and figure it out.
Okay. And there's a question from Radu. Do SSE/AVX work in a VM under VMware or only in a physical server?
Again, that's a spot where we actually call the CPU ID instruction. So if the CPU ID instruction is not intercepted by the VM, and I don't know what VMware does off the top of my head, if they don't intercept that CPU ID instruction and tell us no, then if we find it, we will use it. And actually, part of this actually comes from Windows directly. So Windows 2012 R2, I believe, for like the encryption stuff, they actually do the same thing. So it's not something that just SQL's doing. And so if you just put on Windows, I'm pretty sure it's 2012 R2, and SQL, it doesn't matter if it's SQL 12, 14, or 16, in some of the encryption paths, because we're just using the API just picks it up and does it. So it's not just a SQL thing that does it. We actually take advantage of it in other places where we can do additional compression, additional work for column store and bulk and that sort of thing. But as long as the CPU ID instruction returns that it's available, it should use it.
Good. And there's a suggestion from Peter Tran. Can you ask Bob to update the deck to indicate which of these enhancements are already baked into Azure?
Everything.
Right.
Everything we do goes to Azure before we actually put it in the box. So
yes.
Starting a couple years ago, they actually made a change, and everything that we ship outside in the box has to have been deployed to our internal Azure clusters. So all this stuff is available there. Now, some of the feature sets you may not be able to use yourself. For example, you probably are not using, when you go to Windows Azure SQL Database, you don't use always on with the Azure SQL Database. That's you don't get to set that up. However, certain SKUs internally, we actually use always on behind the scenes to actually do the replication for the triple replicas for you. So even though you might not see directly that you're using always on, we're actually using all these enhancements, and they're already been running for months inside of Azure, which actually is pretty exciting to me, because this is the first release that I can actually say doesn't matter how many, I shouldn't say it that way. We love to get feedback from customers. We love to tap customers. We like these engagements, but sometimes that's been a little dicey, because which customer can you convince to go to production and actually run a production workload on something that you haven't shipped yet that's not RTM, and you get into all those discussions where that Azure helps take part of that away from it, because we are our own production and we're running in production, and we have millions of databases that are running on top of this. So if we break it, we got to fix it pretty quick anyway, or we're up at night, and that simply goes there. We actually have additional things that we do internally, like we call it A/B testing. We actually have clusters internally that are just for testing. So when we actually will sometimes create a fourth replica of a database and put it on this cluster. And when you submit a command for your query, we will actually submit it to that cluster as well. And that cluster might be running the newest bits and just doing and making sure that we don't crash, that we don't corrupt data, that the performance is right, and all that stuff. We rotate around and do things like that just to see what's going on, where it's safe to do. Clearly we can't do it with certain databases and certain customers and certain SKUs. There's a limit to what we can do there. But all that stuff has already happened on top of all the 16 stuff.
Right. I think based on the time, just one last question. There's a question about SSE or AVX. Do the hardware-based vector instructions take advantage of different versions of SSE or AVX that particular CPUs might support?
So I have to go back and look, because I haven't looked at this code for about 6 months. I thought it was SSE4, and I want to say AVX3, but I could be wrong on that one. I'd have to go dig that out again. It's been 6 months since I looked at it.
Yeah, I think probably a blog post would help. Yeah, I believe.
I'll take a note on that one.
Yeah, wonderful. I think now we are almost nearing to the end of the session. So I would like to just to say, don't forget, make sure you are tuned in for the next session, which is Column Store Technology Improvements in SQL Server 2016 with Nico Neuberger. So where we have, in terms of, I would like to thank you all for attending, and I hope this will be much more useful in terms of that, and we look forward for further improvements in SQL 2016 and blog post from Bob Dorr. Thank you all.
Thanks for attending. It was great.
Thanks.